So it's good to go?
And you're live. Go for it.
All right. Good afternoon, everyone. Welcome to the Robotics Institute seminar. It's my great pleasure to introduce Professor Zhao, Professor Xuanhe Zhao from MIT. So Professor Zhao is a professor of mechanical engineering at MIT. And the mission of his lab is to advance science and technology between humans and machines to address grand societal challenges in health and sustainability. And Xuanhe is widely recognized as a pioneer in the field of soft materials, especially the design, synthesis, mechanics, and also device applications of those very cool materials. So Xuanhe is a Web of Science highly cited researcher in past few years, and also he has won many awards. He didn't put those in his bio, but through his website, I think he won the NSF Career Award and many research awards from different professional societies like ASME and the Society of Engineering Science, and etc. So besides his very cool research, Xuanhe has been very successful in translating his research into real practical impact. So he is a co-founder of a spin-off company, Xuanhe, which has focused on translating bioadhesive technology for clinical applications. He also have 10 patents licensed to different companies, and those patents has contributed to a few FDA approved and widely used medical devices. Today, I think Xuanhe will talk about his research on soft materials and systems, and also the application of those materials and systems to health and sustainability. So without further ado, I will pass the floor to Xuanhe. And thanks for coming, Xuanhe, and thanks for making this seminar happen.
Yeah, thank you so much, Xinyu, for the invitation and the very kind introduction. Nice meeting you, everyone. Today, I'll talk about soft materials mechanics for health and sustainability, Xuanhe Zhao. So, the conflict of interests, I co-founded Xuanhe. I received royalty from CRS, and I will discuss results related to both companies. So this is the mission of my lab, merging humans and machines, right? Over the last century, we see great progress in terms of engineering and understanding the human body, medicine, biology, genetics. These are the examples. Similarly, in the domain of machine, right, we see great advance in semiconductors, electronics, computers, internet, robotics, AI. This list goes long. However, there's a huge gap in between, right? And what if we can truly merge humans with machines, right? What can be the potential impact? Better health, that's something we all want. Now, however, if you think about all the way from wearable devices to medical equipment to medical implants, these are machines trying to merge with the human body over a few hours to a few days to months and years, right? Now, over the last few decades, we developed more and more sophisticated machines. However, the interface with the human body remained the same, right? Rigid metals, plastics, ceramics, glass, silicone. These are the interfaces with the human body, has not been changed, right? What if we can design much better interface to truly merge this medical equipment devices with the human body, right? Can we monitor COVID effects on multiple organs at home? Can we continuously image heart diseases with wearable devices? Can we remotely treat stroke within the golden hour, right? These are currently the leading causes of global death, right? Can we make this, impact on human health? Then another impact, right? We have 86 billion neurons in the brain, right? On the other hand, we have supercomputers with huge computational capability. However, the state-of-art brain-computer interface is only with around 3,000 neurons due to this very weak interface between the brain and the computers, right? Now, if we design much better human-machine interface, can we interface with a million neurons in a living brain to better understand the intelligence, right? Now, if we think even further, right, no matter from recent movies or even from recent realistic examples, we know that an essential component in future AI, robotics, VR is human-machine interface, and that will impact the future of humans and the society, right? So now these are some of the potential impacts. What are the challenges? It turns out this is a grand challenge in materials, mechanics, and biology, right? Due to these fundamentally contradictory properties, right? Human body are mostly based on soft, white, and living materials, right? Diverse tissues and organs, right? On the other hand, conventional machines are most based on hard, dry, abiotic materials, right? How to really merge them together, right? Now, so let's take a closer look at the different components of the human body. Now here I plot different components of human body as a function of their rigidity. You can see, except teeth, bone, and nails, all other components are actually soft material. Their rigidity ranging from 1 kilopascal to 10 megapascal. They are also white, containing 70 to 90% water. They are also living. They can grow, sense, respond, self-heal. Also very robust. Under millions of cycles of load, these tissues and the organs maintain their robustness and well-being, right? So with this understanding, we propose a new strategy, a new interface to merge humans and machines, jellos, right? We propose, let's design soft materials, right? With very similar mechanical and physiological properties as different components of the human body. Use that to form long-term, high-efficacy, even non-fibrotic interfaces with different tissues and organs of the human body. At the same time, this soft material is also part of a machine. You can embed or implement these rigid machines, such as sensors, actuators, even computer chips in this soft material interface, and use this soft material to truly merge humans and the machines, right? We wrote a few review papers to really discuss this vision, right? This is a very bold, even seemingly crazy vision, right? Now, in order to achieve this vision, we need to design extreme properties of soft materials, right? So this is a piece of jello, right? We want to design this to be part of a human body, part of a machine. So this jello, we need it designed to be tough, strong, fatigue resistant under millions of cycles load, adhesive to both human body and the external machines, active so it can interact with organisms of the body, electrically, optically, acoustically transparent between the human body and machines, right? For traditional hard material, steel, ceramics, we know how to design these properties, but for soft materials such as jellos, hydrogels, we really need to design new principles, new understandings to design these extreme properties, right? Now, my group has been working in this field around 10 years, right? We actually summarized the understanding and the knowledge, even lots of protocols on how to design this extreme properties of soft materials in this recent review paper. If you are interested in this, you can take a look. In summary, unconventional polymer networks will give you extreme properties, right? Conventional polymer networks, right? For example, this kind of long chain polymer covalently and randomly cross-link into a network. They give intrinsically coupled and limited properties, right? In order to achieve these extreme properties, you need to design this kind of unconventional network, including unconventional polymer network interactions, such as reversible bonds, entanglements, many of these, unconventional interactions, or unconventional polymer network nano architectures, different from this randomly cross-linked networks. You can form nanofibrous networks, interpenetrating networks. So this list goes long. And then interaction, a combination of this unconventional polymer network interaction and architecture that can give you the extreme properties, right? If you want to know the details, you can take a look at this review paper, right? In today's talk, I want to use two examples really to illustrate the impact of soft material mechanics, right, on health and sustainability. The first example is soft medical robots, and I will discuss one specific example, stroke. Right? Stroke is a globally #1 cause of long-term disability, #2 cause of death, 15 million cases per year. Basically, 1 in 4 adults, right, in the audience, right, in our lifetime will have a chance to develop a stroke. So that's the potential impact, right? Now, stroke is also reversible. If you treat stroke within this so-called golden hour, right, a few hours after the occurrence of stroke, then it's reversible. However, if you miss this golden hour, then time loss equal to brain loss, right? How to treat stroke within this golden hour, right? So this is the standard of care. This is called a thrombectomy. So these are neurointerventionalists or neurosurgeons. They will insert this long guide wire all the way from the femoral artery of the patients on the leg all the way to the brain, and they use this guide wire to help clear the blockage, treat the stroke, right? Then you may ask, right? There are lots of vasculatures, right? Very complex vasculatures. How can I navigate during this process, right? So it turns out the tip of this guide wire is this J shape. It's J-shaped tip, and then the neurosurgeon can rotate this guide wire outside the body. This J-shaped tip will rotate inside the blood vessels to navigate this guide wire, right? So that's the basic mechanism. You can see this is really an art, right? It takes a very long training time for those neurosurgeons, 4 to 7 years, right, in order to master this, art, right? And in return, this neurosurgeon, they only work in large hospitals, right? This is called tertiary stroke centers, right? They are not available, especially in rural areas, right? In large cities such as Boston, Toronto, the patients are lucky, right? They can go to these large medical centers. However, for patients, for example, in Maine, New Hampshire, in the United States, they need to be helicoptered in to these large hospitals. But during this transportation, you may already miss this golden hour, right? Therefore, these heroic doctors, right? They suffer a lot. They suffer from accumulated radiation, right? Because you need an X-ray to observe the location of the guide wire, the location of this, blood vessels, right? Then for the patients, is one time. For the neurosurgeon, is their whole career, right? How can we address these intrinsic challenges, right? We propose this highly operated, even autonomous robots, right? To remotely treat stroke, right? So this is the design of the robots. It's based on soft material. So the body of the robots is based on elastomer with this hard magnetic particles embedded in this elastomer. Imagine these are small magnets inside this elastomer, right? And then when you apply external magnetic field, this elastomer, this robot can bend on demand. So that's the design. And the outside of this robot, we coated with this hydrogel skin, right? This is a soft interface with the human body, really to dramatically reduce the friction to make this robot even softer. So that's the main idea for the design of this robot, right? Now, then in order to design and control these robots, we actually need a fundamental mechanics. We really need understanding how these robots deform. That's so-called magnetoelasticity, right? So this is the deformation gradient. This Jacobian represent the change of volume, and we need to discuss stress. We need to use stress, magnetic field, magnetic flux, body force, Helmholtz free energy density, right? So use these parameters to really formulate the problem, right? Then in terms of governing equations, right, is the equilibrium condition in terms of stress and the magnetic field and the magnetic flux, right? So these are formulated already in Maxwell and Gauss, right, decades ago, right? So then in terms of the constituted law is the work conjugation. The nominal stress is work conjugated with the deformation gradient. The nominal magnetic field is work conjugated with the nominal magnetic flux, right? So these are the governing equations, right? We made one contribution in this field. We propose a specific constituted law for this hard magnetic soft material, right? You can see this is the relation between the magnetic field and magnetic flux for hard magnetic material, right? For this magnets, right? You can see it's quite complex. However, for the soft robot, they only operate within this domain. So this is the actuation field regime, right? It only works in this domain, right? Then to the first order of approximation, we linearize the relation between the magnetic field and the magnetic flux, right? You can see this is approximately linear, but they were shaped by a factor. This factor is this residual magnetic flux due to those small magnets, already polarized magnets, right? So that's due to fabrication, due to the magnetization of this material, right? Then how to determine the slope of this, these two lines, right? So it requires some physics, right? The physics is this. The dipoles of this hard magnetic material, neodymium iron boron, has been saturated, right? Because you already magnetized them. Then if you measure the magnetic permeability of air is mu0, of this neodymium iron boron is 1.05 mu0. Polymer is also mu0. Then the whole magnetic robotic body will have a very similar permeability as air, right? Then the beauty is now after you apply a magnetic field over this soft robotic body, the hard magnetic soft material do not perturb the applied magnetic field in space. Then you really decouple the magnetic field and the deformation, right? You only calculate this applied magnetic field once. And then once you introduce this soft robot, this hard magnetic soft material does not change this applied magnetic field. So that's the beauty. Then you can calculate the deformation, right? With this understanding, we further, you calculate. This is the Helmholtz free energy function of this magnetic component, and then you can do duration. Eventually, you can calculate applied magnetic stress due to this applied magnetic field on this, soft, hard magnetic soft material, right? So you can see, take a look at this equation, right? The B applied is constant, right? Because you know what's the applied magnetic field, either from electromagnets or from a permanent magnet, right? You also know what is this residual magnetic flux, because that's due to fabrication, right? Due to initial magnetization, right? The only unknown is this F deformation gradient. Then you can, implement this, additional stress term in Abacus, in whatever finite software. You can calculate the whole coupled problem as an elastic problem, right? Because the only unknown is this deformation gradient. So you convert this coupled problem into a simple, elasticity problem, right? With that, so here, for example, we calculate the bending of this, soft robot, this beam, right? You can see this is simulation results. This is experiment results. We also have theoretical results. You can even use a, analytical equation to predict the deformation of this beam dead on with each other, right? You can see beautiful matching between the experiments and the simulation, right? Many students are interested in this field of soft robots. However, we also know soft robots is extremely challenging to model, to simulate. I would say this hard magnetic soft material or hard magnetic soft robots really give you an opportunity to develop very quantitative model to simulate the deformation of this robot, right? Then with that capability, now we want to design the most agile hard magnetic soft robot for endovascular surgery, right? Then this is actually a clinical problem. How do you define agile, right, for endovascular surgery, right? In order to work on this problem, we collaborated with Dr. Aman Patel, who is the director of cerebrovascular endovascular neurosurgery at MGH, right? Now, according to Dr. Aman Patel and other neurosurgeons, right, the most agile robot for endovascular surgery means the robot, right, can reach the largest workspace, right? The tip of this robot can reach the largest area, because then you have the highest flexibility to navigate to the direction, to the branches you design, right? That makes sense. Then with this understanding, we convert this clinical problem into a scientific or engineering problem, right? The question is, now we can design the voxels, right? Each voxel of this soft robotic body, right? We can put more magnetic particles or fewer magnetic particles. We can design the polarization of each voxel, right? Then the goal is to achieve this largest workspace, right? So that's a design problem, right? So we solve this design problem based on model. So now you see the power of this model, right? Because we don't need to do experiments. With this model, we can do thousands of simulation on random patterns of these voxels, right? You can see these are really random patterns, right? Then we can use either genetic algorithm or even machine learning algorithms, for example, GAN, right? So use that to really to generate the best all the optimized patterns of this polarization to give you the largest workspace. So this is the final results, right? So both algorithms actually converge to these results. You can see at the very tip of these robots, you have a high polarization. At the center of the robot, actually you have zero polarization, right? Then around the end, you have another high polarization. This design actually very counterintuitive, but it will give you the highest workspace, right? If you do experimental trial and error, it's extremely challenging to come up with this kind of design. But with the capability of model and simulation, now we can do this design and we can achieve this optimized design, right? Then with that, now let's fabricate or let's manufacture this. We actually develop a new 3D printing method, adopting the direct ink writing method pioneered by Professor Lewis at Harvard, right? So basically, we design a new ink. You can see this ink has this soft material matrix, and within the soft material matrix, we disperse this hard magnetic particles. These are like small magnets, and then on the nozzle of this 3D printer, we couple an electromagnet. The electromagnet can be turned on and off, and once it's turned on, they actually reorientate, right? They polarize those magnetic particles, right? Then you actually polarize the printed filament in 1D, or you can polarize them in 2D or even 3Ds, right? You can print very complex soft robots like this, right? But in this application, we actually harness this 3D printing system to print this guide wire robot, right? This is really just one filament can constitute this guide wire robot, right? Then with that, now let's try this robot in this real size silicon cerebrovascular phantom with simulated blood, right? This phantom was from 3D printing the real blood vessels of our patients. You can see these are the locations for the aneurysm of these patients, right? Now look at this beautiful navigation under magnetic field control, right? So really, there's no need the J-shaped tip of this guided wire robot anymore. You don't need to rotate this guided wire anymore. Just very smooth navigation, right? Then with this, now we build up a full system, right? So you can see this is a full system for highly robotic neurovascular intervention, right? The system has a C-arm for imaging of blood vessels and the guide wire. Then there's a robotic arm holding a magnet to apply the external magnetic field to bend this guide wire on demand. And then we use this joystick controller to control this robotic arm to control the location of this magnet. Then we have another system, right? This is advancing a retraction unit to control the advance and the retraction of the guide wire, right? You can see you can push these buttons so the guide wire can move forward, move backward, right? Beautiful. So, but this is now the robotic control, right? Advancing on retraction is controlled by another unit so that you can decouple the task of navigation and the task of advancing and retraction. Right? So then let's see some clinical relevant cases, right? This is a case operated by a neurointerventionalist. You can see remotely, right, or in another room, in future, even in another city, right? This is a case of aneurysm, right? This, bulging out on the blood vessel, right? So for this kind of aneurysm, usually people use, a platinum coil to coil it up to form this aneurysm coiling to protect the aneurysm, right? If it's not protected, then it can burst. It can form a hemorrhagic stroke. You can see there's a beautiful navigation of this guide wire to this target aneurysm. And then in the second step, the robotic system delivered this, microcatheter to this target aneurysm. Then you withdraw the guide wire, right? Then in the third step, you deliver this, platinum coils to this targeted aneurysm to coil it up, right? And by the way, the whole process is visible in VR environment, right? This VR environment guaranteed that this robotic arm with this magnet will now collide with the brain of the patient. Always there's a C-arm fluoroscopy, right? This already programmed in the code, so it cannot collide with other objects in the cath lab, in the surgery room, right? So beautifully. So then this is one treatment. This is another clinical indication. This is a clot, right? If you do not retrieve this clot, it will form ischemic stroke, right? Similarly, right, with this robotic system, we can deliver a stent retriever. It's like a fish net to capture this clot to withdraw it. This treatment can be done in another room or in another city, right, in future, right? So that's that. Then not only that, we actually move this to live animal models. This is the live pig model. So this is a porcelain branchial artery in the flexed, forelimb position, right? So this is the well-established model for the, certain arteries inside the human brain, right? So this is an established model. Right? You may hear this beeping sound. That's the heart beating of this pig. So it's really a live pig. You can see this real-time navigation of this guide wire in the blood vessel, and this is the control, right? In the VR environment, so you move the magnet towards the guiding direction to bend this guide wire, and then this guide wire move inside the blood vessels in this live. So the neurosurgeons is doing the operation in another room in future. So that's that. Then let's just compare the performance of this robotic treatment with manual operation, right? Number one comparison, much faster learning curve than manual operation, right? Conventionally for manual operation, the training time is over 4 years. With this robotic system, surprisingly, only took the neurosurgeon around 1 hour to get familiar with this robotic system, right? You can see N equal to 6, right? For 6 neurosurgeons, very quickly they become experienced within 1 hour. Of course, these neurosurgeons are already familiar with the fluoroscopy, already familiar with the vascular system of the brain due to previous study, but it's also still very amazingly, short time for them to achieve this experience level, right? Only a few hours, right? So that's that. Then now another comparison is, the performance, right? Compare the performance of this robotic manipulation and the manual operation, right? You can see from this video, you can clearly see the difference, right? Here is a manual operation, right? You need to rotate this guide wire, and you can see due to this J-shaped tip of this guide wire, unavoidably this guide wire will touch the blood vessel and even sometimes touch the aneurysm, right? So, but with the robotic system, you can see here, beautifully, you can smoothly navigate this in the vasculature system without touching aneurysm or the blood vessel, right? And this is the quantitative results, right? You can see, pay attention to this figure, right? For this manual operation, no matter after how many times of trials, the neurosurgeon still have this undesired, steering, right? Touching the blood vessel or touching the aneurysm, right? It's intrinsic because the shape of this guide wire is J-shaped. For the robotic system, very quickly, it reduced to 0, right? So just amazing performance, right? Now, what's the next step, right? So we are moving even further. We are trying to further reduce the cognitive burden of neurosurgeons to make this system to be autonomous or semi-autonomous, right? So here's the idea, right? We have, high resolution medical imaging of the location of the blood vessel and the guide wire, right? Then this become an inverse problem, right? A desired trajectory of the guide wire, the current position of the guide wire. Then the problem is what magnetic field I should apply to bend the guide wire from the current position to the desired trajectory, right? This is an inverse problem, right? Inverse problem is difficult to solve, but we can solve it with machine learning algorithm, right? For example, a deep reinforcement learning, right? So we do millions of simulations, literally, of different scenarios, right? And in these scenarios, we optimize the applied magnetic field. Then we feed all these results from simulation to this neural network, and then use neural network to do interpolation to give us the control variable, this applied magnetic field. So that's the idea. And with that, now we can really obtain, optimized applied field for this navigation. So that's that. With that, let's see some preliminary results. This is, another phantom. You can see in this process, there is no neurosurgeon involved. The whole process is autonomous, right? You can see the image processing will identify these critical locations, right? Very similar to drive a Tesla. You will identify the critical locations, other cars or pedestrians, right? You identify that, then the neural network will do a calculation to figure out, apply the magnetic field to control this robotic arm to the desired location to accomplish the navigation, right? This is a simple case, but you can see the potential, right? Really, we are converging to the point to make impact with robotics and autonomy in the field of health and medicine, right? Now, so here's the vision, right? So we believe soft robotics plus AI and plus high-speed communication, such as 5G, will really enable or empower future precision medicine, right? So here's the reason, right? This is very different from autonomous drive, right? There are many societal issues for autonomous drive, but for this autonomous or semi-autonomous robotic system, all stakeholders are on board, right? As a scientist, right, I do science for curiosity and for societal impact, right? When I develop this equation, I don't know what can be the impact, but once I know this may help a neurosurgeon to treat a stroke remotely, I'm all in this game, right? For neurosurgeons, right, we are not replacing them. We are actually empowering neurosurgeons, right? They can save more lives, safer, faster, remotely, with much less training time, right? They are fully on board. For patients, time loss equal to brain loss. You can see all stakeholders are on board. And the technologies, right, all the way from medical imaging to robotics, to material, to mechanics, are converging towards this point of realistic impact. So I'm very confident about this vision of a remote stroke treatment, right, with the help of modern technologies. And not only that, I also want to propose a fundamental challenge in science and technology to the whole audience, right? Now we achieve great progress of genetic editing of cells on molecular level, right? For example, CRISPR is an example of a recent breakthroughs. However, currently we do not have a robot can minimally invasively to edit the full human body on a cellular level, right? For example, remove a tumor from any desired location of the body, minimally invasively, to deliver drugs, cells, even CRISPR to any desired location of the body, minimally invasive. Currently, we do not have such a robot, but can we achieve, such a robot in the future? Now, with this soft, guided by robot, I think probably there's a possibility. And if the community work together, right, develop other kinds of miniaturized robots, right? Because you can see we can miniaturize this robot all the way down to the length scale of 10 micron, right? That's the size of most vasculature, right? You can basically navigate this robot to most of the locations of the body, minimally invasively, right? Then with that capability, you can do many other follow-up treatments, right? For example, remove something or deliver something to those desired locations, right? So if the community, right, work together, I really think we can address this fundamental challenge in science and engineering, right? Okay, let me switch gear to discuss another topic, wearable imaging, right? So I'll begin with this stretchable electronics, right? We see a great progress, great success in this field of stretchable electronics. Basically, people develop thin stretchable devices that really conform to the skin, right? You can see beautifully conform, and they can measure EKG, EMG, EEG, heart rate, temperature, even sweat. Right? Many pioneers, for example, Professor John Rogers at the Northwestern University, and many other pioneers in this field. This is great. However, this modality is not for imaging deep organs, right? But we know how important imaging deep organs is, especially if we can make that to be variable, right? So now, indeed, there are some recent development in terms of stretchable ultrasound, trying to image deep organs, right? Great progress, for example, Professor Xuanhe at UCSD is leading this field. However, ultrasound, stretchable ultrasound, there's an intrinsic challenge. The challenge is here, right? Ultrasound imaging requires accurate transducer positions, right? You need to know exactly what's the location of each transducer on this stretchable patch. However, when you conform this stretchable ultrasound probe on the skin, right, you really distort the location positions of this transducer. Then that can induce significant imaging error. So that's the challenge, right? Then also stretchable ultrasound probe, right? Because these are rigid PCTs, they are prone to mechanical failure. Right? These are intrinsic challenges, right? So my group actually last year we proposed a fundamentally different approach, right? The approach is this, right? We call it a bioadhesive ultrasound, right? You can see now the ultrasound probe is not stretchable anymore. We use a thin, rigid ultrasound probe, right? So because the rigid ultrasound probe can really give a high performance image, right? Then you may ask, how can you conform this rigid ultrasound probe to the flexible skin, right? You can see the skin is also, linear curvature. How do you conform the rigid probe on the skin? We use this soft bioadhesive couplant, right? You can see this is a soft couplant, right? This is a hydrogel elastomer hybrid. You use that to conform with the skin, right? That give you good skin adhesion and conformation. At the same time, you adhere this thin, rigid ultrasound probe to the skin, right? Then this ultrasound probe can insulate the string, right? The skin can deform, the soft coupling will deform, but the insulated string from the skin to the ultrasound probe. It can also give you functional communication, electrical, acoustic, optical, biological, chemical, many communication, right? So that's the key idea. Now the device is rigid, right? So that's the key difference, but you use a soft bioadhesive couplant to really adhere the device to the skin. Then with that, so we transform this conventional, ultrasound imaging, right? This is a very powerful imaging modality, right? But you need to do this in a hospital. Usually give you a snapshot, static image, right? So we transform this, very powerful ultrasound imaging modality into something like this. So you can see now this is wearable. You can wear this at home or in hospital. Now the imaging is not a snapshot anymore. It can be long-term. You can image deep internal organs over days. It's hand-free. Now you don't need a hand to hold this ultrasound probe anymore. And the subject is under dynamic body motion. You can run, you can do all kinds of sports. You can still image the deep internal organs. So that's the key idea, right? Then fundamental mechanics, right? So number one, how can you guarantee the adhesion of this device on the skin is robust, right? So then here we do this mechanics calculation, right? We calculate the energy release rate. This is the driving force for debonding of this soft couplant from the skin, right? You can see this energy release rate is a function of the couplant thickness, right? When the couplant is thin, the energy release rate is high, right? The maximum one is when the couplant thickness becomes 0. Right? You literally bond this rigid device on the skin. That will give you the case of the highest energy release rate. But even for that case, we have an analytical solution, right? By this solution, right, we can put in typical numbers, skin modulus, size of the device, skin deformation. Then you can evaluate, right? It turns out the maximum energy release rate is on the order of 20 joule per meter squared, right? This is much higher than the adhesion energy of physical attachment, right? For example, if you only physically attach this device on the skin, you debond because the physical attachment only give 1 joule per meter squared. However, we can design interfacial toughness, this adhesion energy, to be way over 100 joule per meter squared, right? That's a factor of safety over 5 to guarantee the robust adhesion of this soft couplant on the skin, right? How to design that? Then I will put on my hat of a material scientist, right? We design this hybrid physical and chemical bonds between this soft couplant on the skin, right? So there are some permanent covalent bonds, some physical bonds, really give this a very robust adhesion of this soft couplant on the skin, right? And then here, right, some very interesting design, right? In the center of this couplant, we have a piece of hydrogen because we want this very high acoustic transmission capability, right? Hydrogel turns out to be, give you very high transmission capability, very low attenuation, right? So the result is here, right? We compare the attenuation coefficient, the damping coefficient of diverse couplant, right? So this is the bioadhesive ultrasound couplant. You can see extremely low, actually the lowest, due to this better adhesion, better coupling, and due to this hydrogel elastomer hybrid design, right? You can see many other couplers, right? Much higher, this attenuation coefficient, right? Then we also designed the ultrasound probe, right? This is a thin, rigid ultrasound probe, right? We actually use a 3D printing to do lots of design and optimization. Eventually, we converge to an optimized design. You can see for this probe, we can wear it on the skin over 48 hours, right? Because the power of this probe is very low, you do not heat up. You can see you maintain the same temperature, right? Over 48 hours, right? Now, how low this power is, let me compare this with the power of Apple Watch. Apple Watch power is 100 milliwatts. The power of this bioadhesive ultrasound probe is only 10 milliwatts, right? Even much lower than Apple Watch. Then with that, let's discuss some results, right? This is for the first time, now we have long-term continuous imaging of the lung over 48 hours. You can see, this I present, the results every half an hour, but you can really continuous image the lung over 2 days, right? Now, what can be the potential impact, right? Especially for many COVID patients, right? After patient test COVID positive, now we can send this COVID patient home, but adhere a patch, this bioadhesive ultrasound patch on the chest of this COVID patient. For the majority patient, right, over days, their lung will look like this, right? Thin, smooth pore lines, right? This indicate, no lung infection, right? No symptom, COVID symptom for the lung. So these patients, right, they can stay at home, right? That's okay. Right? For a few patients, right, especially those highly risk case, you may observe this phenomenon, right, after a couple of days of COVID, right? The pore line may become thickened and irregular. A line may condense. This indicates lung consolidation, potential pneumonia, right? This indicates potentially, possibly COVID symptom, right, due to COVID, right? Then at this time, the hospital can send this patient a warning. The patient should go to hospital for potential treatment, right? That's the potential impact. And with that, this is way before the blood oxygen level of patient getting low, right? Because this is the symptom before the blood oxygen getting too low. Then really you can have early treatment for the patient, for this COVID patient. So that's the potential impact. Then another one is long-term continuous monitoring of blood pressure waveform, right? We know around 1 billion adults, right? 22% of the global population have hypertension. Hypertension is the most important preventable risk factor for premature death, right? It's highly desirable to continuously monitor your blood pressure level over days, right? On the other hand, we know how cumbersome the blood pressure cuff is, right? You need pump pressure, right, in order to measure your blood pressure, right? It turns out the blood pressure level is correlated with the diameter of this chaotic artery, right? Then you can really stick a pulse patch around the chaotic artery, right? Then you continuously measure the diameter of this chaotic artery, calculate the blood pressure, not only values, also a waveform. You can see, the whole waveform of blood pressure. And in addition to that, as some byproduct, you can also do Doppler mode of imaging. You can measure the flow rate, right? At the same time, measuring the blood pressure, right? What can be the potential impact? So here, for example, this is my blood pressure, right? After doing some sports, you can see there is a spike of blood pressure. This is another sports. And then, when I give this talk, right, I got really nervous because there are many audience online, right? So I got a high blood pressure. Then at this time, my cell phone maybe send me a warning, I should either calm down or take some medication, right? That's the potential impact, right? Really in-loop management of your blood pressure, right? That's our vision of this field. Then another one, long-term continuous imaging of, heart, cardiac dynamics, right? We know cardiovascular disease are #1 cause of global death, right? Apple Watch, for example, made a breakthrough in this field. Apple Watch can, continuously monitor the EKG of, patients, right? However, it turns out the EKG can only diagnose around 20% of heart attacks. Majority of heart attacks requires this kind of imaging modality, for example, ultrasound imaging or other imaging modality. Now with this bioadhesive ultrasound, you can have over 48 hours long-term continuous image of the heart, right? Once the patient felt chest pain or uncomfortable, at that time, they can transmit the imaging data to a clinician for real-time diagnosis, really at the moment of occurrence of this symptom for the diagnosis, right? So that's the potential impact. Then another one, all right, this is muscle, long-term real-time imaging of muscles, right? It can tell you how much exercise is sufficient or too much, right? We don't know. Sometimes we tend to do the exercise, but the ultrasound actually can tell you the microstructure change of your muscles during sports or after sports, right? It may be able to tell you what's the optimal time and the point to stop the sports, right? So potential impact on sports medicine, rehabilitation, and many others. Right? Long-term real-time imaging of gastrointestinal tract, right? So this is the image of my stomach after drinking this morning coffee. This is image after the morning coffee has been digested, right? Now you can really image this in real time, right? Not only the stomach, you can also image bladder and many other organs, right? Imagine the potential impact, right? So, and also I want to emphasize, all this is under dynamic body motion, right? For example, here is you can do jogging, you can do bicycling, right? The imaging quality are similar because you literally adhere the ultrasound probe on the body. Now you don't use a hand, hold it, or you don't, just simply put a patch on the body. You adhere it on the body robustly. So that's the really you can afford all kinds of dynamic body motions, right? So it turns out the soft material mechanics can be as hot as AlphaGo and the CRISPR, and I have the data. Right? This is Ometric score after we published this bioadhesive ultrasound paper. It's really similar to the AlphaGo paper by DeepMind, even similar to the CRISPR paper by Daldana and Carpenter Labs. Right? So we are really proud and we are really happy that the whole society really interested in this wearable imaging capability. And not only that, right? Very reputable, world-leading clinicians in the field of digital and personalized healthcare medicine really appreciate this technology. So here is Dr. Eric Topol, our COVID hero, right? So I just quote his comments. It's a very impressive new frontier about how we can use ultrasound imaging continuously to assess multiple organs, organ systems. It's a new window into the human body that we have never had before. This is anatomy. This is very different. We have never had a sensor with a continuous anatomical imaging, right? So really, I think the experts in this field also appreciate the potential for wearable imaging, right? Then where do we go? So here's our vision, right? This is the state of art, wearable devices, right? For example, Apple Watch give you EKG, right? Usually the data are linear data, right? Measuring EKG, EMG, right? This kind of linear data, right? Now, in the future of wearable devices, it can be continuous imaging of diverse organs, right? In addition to those linear data, you really give images of deep internal organs, right? That will give you another level of information for diagnosis for long-term continuous monitoring, right? Then with this huge amount of information, right? How do you analyze them? The AI will play an important role, right? So you can see this bioadhesive ultrasound with AI will really empower, the future precision medicine, right? You will, transmit those long-term continuous images of diverse organs, maybe to the cloud, and the cloud will do analysis, even do real-time diagnosis, right? So here's a few potential impact, right? Long-term high-resolution imaging of health diseases of diverse organ system, chronic conditions, at-home monitoring of COVID, long COVID patients, tumor development, right? Really long-term continuous monitoring of tumor development, fetal development, preterm birth, women's health, right? In addition to really discussing, this diversity, why don't we develop technology for diversity, right? Then brain development. So this is my dream and my vision. I want to make ultrasound a wearable commodity for global health, right? We know ultrasound is such a powerful tool for diagnosis, right? There is no reason you have to go to hospital, clinician's office to do such a diagnosis. I really, if we work together, we can make ultrasound a wearable commodity for global health. So then also I want to propose another fundamental challenge in science and technology, right? So currently we can achieve super resolution imaging of single cells, right? For example, storm and many other imaging modalities really pioneers in this field. However, human body is much more than a single cell, right? We have billions of cells, multi-billions of cells, trillions of cells. And also these cells self-assemble into different organs and organ systems, right? Can we achieve long-term continuous imaging of the full human body, right? Over days and months, right? I believe the potential impact here can be even similar as super resolution imaging of single cells. Now with bioadhesive ultrasound, I think we have hope. Now, even within my life, we begin to observe multiple organs together with this bioadhesive ultrasound, right? You will see extremely interesting correlations between different organs over long term, days to months. Now, if the community work together, I really think we will achieve a full picture, right, of the full body over long term and continuously. That's that. Let me summarize. I discussed the soft material mechanics, right? In terms of fundamentals, it's really about actuation and adhesion, right? For actuation, I discussed this new material, hard magnetic soft material. The beauty of this material is it really gives you the capability of a quantitative model, right? Very simple models can have quantitative modeling of this material under the robots based on this material, right? Then in terms of adhesion, I propose a new strategy to couple devices to the human body, rigid device with a soft bioadhesive coupling, right? You may remember, try to remember these two key equations. I'll read the papers, right? Then in terms of impact, right? So soft materials impact, I really think soft materials can be integrated with modern technology, such as AI, 5G, right? The impact better health, right? Understanding and editing the full human body, the fundamental challenges I propose, sustainable water, food, plastics, environment, energy. My lab is also working in this area, even though I do not have sufficient time to discuss it. The future of humans and society, right? And also I want to emphasize, right? In working in this field, right? we will not stop at a single paper. We will really translate those papers to realistic, societal impact. For example, CRRS license our IP, our technology, on hydrogel elastomer hybrids, and then they make this into more realistic tissue phantom. And this tissue phantom in turn train many clinicians, many radiologists, and these many radiologists may help COVID patients during the pandemic, right? These are the kind of potential impact we want to see this soft material mechanics to make. And also many other technologies we are developing in the lab. We either translate them into startup companies or preparing to translate them into startup companies to make a realistic societal impacts. Acknowledgement, I already acknowledged many students who get involved in this talks. These are the collaborators, right? Professor Pradeep Sharma from University of Houston, Professor Sean Chester from NJIT, Professor Aaron Mooney from UofT. So this is really an ocean project we work together. Then clinical collaborators, Dr. Aman Patel from MGH, Pablo Horker, MGH, Aris Vabs, BIDMC, Rafael Bueno, BWH, Franco Lodolfo, MGH, Christoph Nabzi, a great collaborator, Mayo Clinic, Lehigh Griffiths, Mayo Clinic, really a dream team of clinicians, clinical collaborators. And also thank the funding agencies. Many donors actually donate gifts to my lab to support our research. I want to particularly thank those donors. And with that, I'll take questions. Thank you so much for your time.
Thank you. Thank you, Xuanhe, for the fantastic talk and very fascinating and inspiring. So now the floor is open for questions. Please, for the folks in the room, feel free to unmute yourself and ask questions to Professor Zhao. And for the folks online through YouTube, you can ask questions through the comments, and we will read it to Professor Zhao. Please go ahead. Okay, let me see. I can read one question input in the chat box from Zhao Xin from Jason Lee. Thank you, Professor Zhao, for the wonderful talk. My question is that, in practice, will the blood flow have impact on the navigation of the magnetic guide wire? That's the first question. And my second question is that, given the NDFEB particle, this magnetic particle, encapsulated by the hydrogel skin, how about the biocompatibility of the magnetic guide wire?
Thank you so much. So both are great questions. So the first question is about the blood flow, whether the blood flow inside the blood vessel will affect the navigation and the deformation of this guide wire robot. The answer is yes. But in the designing the robot, we already take those blood flow those effect into account, right? You can see in all the phantom models and even the live animal models, we have either simulated blood flow or real blood flow. You can still easily navigate. One of the reasons is for this navigation, you don't need a very accurate solution, right? You just need a point towards the desired direction. So that gives us lots of flexibility, even in this blood flow environment. So the second question is about the biocompatibility, right? So in the soft guide wire robot, we use neodymium ion boron particles as the magnetic particles, right? How about their biocompatibility? So because those particles are encapsulated in an elastomer body, the elastomer is a polyurethane, extremely robust elastomer. And then we only coat the surface of this elastomer body with hydrogel. So there is no corrosion or leaching out problems per se for those magnetic particles. And just as extra caution, we also coat the magnetic particles with a silica glass layer, if you read the papers carefully, to even prevent any potential leakage. And also we did an extensive, biocompatibility test. We culture cells together with it. Really no biocompatibility issues. Also, I want to emphasize, this is really a short-term in duration inside the body, right? It will not stay in the body more than a few minutes. You only navigate it in the body and then you withdraw it. So with that, we are confident this is a quite biocompatible solution for this thrombectomy endovascular treatment.
Cool, multi-layer of measures for improving the biocompatibility. Any other questions? I saw. Any questions? Kimberly, do you see any questions from the YouTube comments? I do have one question, Xuanhe, before others came up with questions.
Sure.
For the ultrasound chip, how long it could last in terms of the energy? Like, is there any on-chip batteries, or is more like a wirelessly charged?
Great question. Yeah. So for the current version of this, for the first paper, this science paper, we use so Verisonics. Everyone else uses Verisonics. It's a large desktop units to control this ultrasound. So there is no power issue. But so that's number one. And also for this ultrasound probe, the power consumption is 10 milliwatt. That's extremely low. For example, cell phone battery can power that over days, right? So now for the second generation, now we already developed that. That will be submitted soon. The paper will be submitted soon. So that one we have an integrated system. For that system, the power a cell phone battery can power that system over 6 hours for continuous imaging. Now, if you do this imaging, for example, intermittently, one imaging half an hour, then you can also use that, do imaging of the body over days without a problem. Yeah. So, and also, there are other handheld ultrasound. For example, many GE and many other already developed wireless handheld ultrasound. So that's not I would say that's not impossible technology, and we already achieved that. So wireless, long-term over at least 6 hours, long-term continuous imaging.
Very cool, very cool. I saw Luder has a question. Luder, please go ahead.
Yeah, thanks for the amazing talk. This was really inspiring. So what does it cost at the moment to make such an ultrasound probe, and what do you expect for later? How much will this cost?
Very good question, Luda. So the question is about the cost of the ultrasound probe. That's a difficult question to answer in the sense that if it's mass produced, there may be one price. Now currently, the ultrasound probe in terms of materials and supplies is not very expensive. We use a piezo, this bulk piezo ceramic to make the probe, and we either use this lithography or use laser or use 3D printing to manufacture the probe. So that's not very expensive, a couple $100. Then in terms of the coupling, we use very common chemicals. There is no specially synthesized chemical. Well, there are some special synthesized steps, but no particular chemicals. Very low cost. It's it's on the same price as a conventional ultrasound coupler. So this part can be extremely low cost, I would say. Now, then the integrated system, right? If we're talking about all those chips, right? Beam formation, right? This CPU, many other things. That may be another level of cost, right? I would say now then you can compare the cost of that with, for example, Butterfly and the existing point of care ultrasound. Currently, their price is on the order of a couple of $1,000. I would say at least the cost will be lower than that, because there are many other reasons. Because this bioadhesive ultrasound don't need to be general purpose, right? For example, I can have a bioadhesive ultrasound only for heart, only for blood pressure, only for stomach, because it can be specialized, right? Because it's a tag. So we believe we can dramatically reduce the price in future, but we are confident it will be already be much lower than existing point of care ultrasound.
And how many postdoc or graduate student years are already put into this, and how much do you expect that you needed to bring it to the next stage?
Oh, that's a great question. Right. Currently, we have a team of a few students and postdocs. So they work very hard. This is really an idea proposed of brilliant students. If you read the paper, the first author, the co-first author of the paper, who already has lots of experience with wearable ultrasound, he proposed the idea, and then because my group has lots of expertise in bioadhesive, so very quickly, within 1 year, we actually finished the project. Now, in order to really make a realistic societal impact, we believe we need another few years. But because ultrasound technology is relatively mature, we can leverage many existing technologies. We don't expect that to be too long. So, but
yeah, I find this
translation is always unpredictable.
Yeah,
right?
yeah.
So, but we are working hard towards that direction.
No, I find this really a very inspiring example of how things can be pushed forward, and it seems so not simple, but reasonable to do, right? And also to gather that very, very nice data with this, and monitor that many important organs. I think this is really cool.
Yeah, because ultrasound probe is rigid. We don't have all this image distortion, all these issues. So we we have not achieved state of art, existing ultra, but it can be similar because they are using rigid ultrasound probe. We are using rigid ultrasound probe, right? Then we have even better integration with the human body. The bioadhesive mechanism, that's really fundamentally new. Really, I think will potentially change this field. Then with that, now you can really, I believe, enable this variable imaging and vision.
Yeah, it's definitely very fascinating to see so many possibilities of using this variable ultrasound system. You really illustrate many possibilities through experiments. That's really inspiring, I think.
Thank you.
Okay, thanks. Anya, last call for questions, especially for our students. This is a very good chance for you to ask a world expert in the field. So any for questions? Our student maybe just a little bit shy, but anyway, I believe many of them, because I recognize names in the list, many of them has read your papers a lot. So, but anyway, Xuanhe, just to avoid like a delay the subsequent meetings more, maybe we can close now. And thanks a lot, Xuanhe. Thanks again for the fantastic talk.
Oh, thank you, everyone. For,
thank you.
Fred. Yeah, so I just stay here for the follow-up meeting.
Yeah. I think Luder will join you first, then we'll have another professor join you in the same room.
Very good.